In this lesson, Notes 2.1, we're going to be looking at differentiability and continuity. A function f is differentiable if the derivative from the left and right exists and are equal. Remember, derivative, think slope. If the slope from the left and right exist and are equal. Differentiability fails in one of three situations. A graph would not be differentiable when a graph is not continuous. So I have this space here so we can record two different graphs that are not continuous. So we'll call this graph f of x, and I'm going to draw a here-there graph. So this is up here at 1, and this is down here at -1. So differentiability fails when a graph is not continuous. Differentiability means we're looking for the slope of the graph. Okay, this differentiability would not take place at x equals 0 because we don't even have a point there to put a tangent line to. Okay, so we say down here then, f is not differentiable, I'm going to abbreviate, at x equals 0. Another way you might be asked about this differentiability for a graph is you might be asked on what x values is this graph differentiable? Well, if the graph is not differentiable at x equals 0, then it's differentiable at all other x values. So f is differentiable on, and we'll use interval notation, all real numbers except for 0. So let's just choose an x value that's not 0 and just kind of make sure we understand what it means to be differentiable. So let's consider x equals 2. Maybe it's right here. At x equals 2, I'm on this part of this branch right here. The slope from the left and the slope from the right are both 0 because this is a horizontal piece here. And as I get closer and closer to x equals 2 up here, the slope from the left is still going to 0 and the slope from the right is still going into 0. I could have chosen any x value. I just decided to pick on x equals 2, except for x equals 0, because the graph's not connected at this jump discontinuity. So how could you even put a tangent line there? All right, let's look at a second graph. So let's say that we have maybe this kind of cubic graph here, and then all of a sudden we have this point discontinuity. And remember, that's also called a hole or a removable discontinuity. Those three terms mean the same thing: removable discontinuity, point discontinuity, and hole. All right, I'm just going to say that this is x equals 2. I could have called it x equals c for any x value. So can we say that this graph is differentiable? No, it fails to be differentiable at x equals 2. But this graph is differentiable at every other x value besides x equals 2. Remember, if you have a point discontinuity here, how can you even put a tangent line to the graph at x equals 2? Because there's not even a point there to put that tangent line to. All right. So depending upon how the question is worded regarding differentiability, we could say that f is not differentiable at x equals 2. If the question was being asked regarding differentiability, such that if it asked something like, where is this graph differentiable? Then you would say f is differentiable at all real numbers except for 2. So a graph is not differentiable when it's not continuous. All right, let's look at situation 2. When else would a graph not be differentiable? Well, that's when a graph has a sharp turn. So let's look at two graphs that have sharp turns in them. I think the first one's going to be the most obvious. I'm going to look at an absolute value graph. So maybe I'll put it right here. And again, I could call this x equals 4, 5. I'll just call it 2. Notice that this graph is continuous across its whole domain, but this graph is said not to be differentiable at x equals 2. Why? Because the slope from the left and the right, although they exist, they are not equal. And what we mean by that is this. Think about at x equals 2 trying to put a tangent line here. I mean, the tangent line can be all over the place. I mean, it just, it won't work. It just, the tangent line has to be so, close to this function that when you zoom in, you can't tell what's the tangent line and what's the graph. Okay, so this graph, this absolute value graph, although continuous, is not differentiable at x equals 2. It's differentiable everywhere else, except for x equals 2. So let's kind of consider, well, what happens at x equals 1? Well, let's say that we're right here. Okay, so in order for the graph to be differentiable at x equals 1, the slope from the left and the slope from the right as we get closer to x equals 1 is going to be the same. Well, this slope, this is a linear function, so this slope is probably always like -1. And even if I come to this point from down here, from the right, moving up though, the slope's always going to be -1. Likewise over here, if I'm up on a point on the graph of this absolute value over here, this graph is differentiable at this x value because the slope from the left and the slope from the right are always going to be +1. But notice right here at x equals 2, the closer I get to x equals 2, the slope is -1. But right here, if I jump to the right of x equals 2, then I'm looking at a slope of +1. So -1 slope and +1 slope, okay, from the left and right exist, but they're just not equal. So f is not differentiable at x equals 2. But we can say f is differentiable on all real numbers except x equals 2. Well, there's other graphs that may have a sharp turn, except they might not be absolute value, and that's okay. We can have a sharp turn on a piecewise graph. So let's just say maybe we have a part of a parabola, and right here we go, yeah, I'm tired of being a parabola. I'm going to stay connected, but now I want to be a linear function. And maybe it goes straight down like that. Notice this is also a sharp turn. Just for the sake of continuity, I'll go ahead and choose x equals 2 here. All right, well, the slope of the graph exists on all parts of this parabola, okay? But as I go into this x value at 2, the slope of this graph is positive, but as soon as I go to the right of x equals 2, notice immediately my slope is going to be a negative number. So whatever, it doesn't matter, whatever positive slope this is and whatever negative slope this is, they're never going to be equal. And just for the sake of making sure we look at another case here, what if I had decided that instead of going downward like this, maybe I want to change to a straight line, but I still want to go upward? Well, this slope right here needs to be the same as this slope right here. We'll learn techniques for finding the slopes, but if these two values, these two slopes, okay, on either side of x equals 2 aren't the exact same positive number, then we still would say that this graph is not differentiable at that sharp turn. It would be possible for us to transition from a parabola to a linear function, and it's just kind of a smooth transition to where there is no sharp turn, and in that case it would be differentiable. But we're going to have to know other techniques for investigating that, and we will learn that. Okay, but for right now, let's just use the graphs as a visual. All right, so far a graph fails to be differentiable when it's not continuous and when it has a sharp turn. The third time is when a graph has a vertical tangent. Okay, let's consider a cubed root kind of situation, a cubed root graph. Let's say that we have a graph and it's coming in here like this, and all of a sudden it just goes, wow, way up to the top there. It doesn't go backwards, that wouldn't be right, but it just gets so steep right here, it's almost straight. Okay, so somewhere right here at this x value, if I drew in a tangent line, Okay, it would be a line that's tangent to the graph, but it's vertical. Well, what kind of slope exists on a vertical line? Well, a vertical line has no slope or does not exist slope. So remember, a function is differentiable if the slope from the left and right are equal, or they exist and are equal. Well, slope doesn't exist on a vertical line. So this vertical tangent line that has no slope or does not exist slope causes this graph to be not differentiable at this x value. I'll just call that x equals 1, just to mix it up. So vertical tangent line. So we really have to look at the graph and see if there's kind of like this just spike in the graph, and it looks like it's almost going straight up. So for this example, f is not differentiable at x equals 1. But everywhere else, f is differentiable. Oops. I just now realize I'm picking on f a lot. I could call this g of x, and then of course down here I'd have the g's. I guess we just get comfortable with f. But there's 26 letters of the alphabet, so I could have used a different letter. But just know that we're not always just talking about f. All right, let's look at another graph that's familiar to us. It's familiar to us that also has a vertical tangent line. All right, let's think of the square root graph, and maybe I've shifted it right and up or even left and up, doesn't matter. Let me just get a square root graph here. It has an endpoint. What happens is when it leaves the endpoint, we can't see it typically, but it shoots off that point almost vertical, and then it starts heading over with some slow growth here. So I'll call this x equals 1 here, I guess. So this graph right here, the square root graph, is differentiable except for at the x value of its endpoint. Because if we were to look at a tangent line to the graph at x equals 1, okay, actually what we'd be drawing in is a vertical line. And a vertical line has no slope or does not exist. So as you back up on this graph and you get closer and closer to x equals 0, you can see that your tangent lines are becoming vertical. All right, so graphically by inspection, we can determine if a graph is differentiable at certain x values by considering that a graph is not differentiable when it's not continuous. It breaks in the graph. There's no point there to even put a tangent line to. Okay, when a graph has a sharp turn, because the slope from the left and the right, although they exist, are not equal. And then the third case is when you have a vertical tangent line. This is the one that's most easily forgotten when we go back and review this later in the year and you're asked, what are the 3 cases where a graph fails to be differentiable? We often forget about the vertical tangent line. There are lines there, tangent lines there, it's just that they have no slope. So that's what causes the graphs to be not differentiable at those x values. All right, and then to wrap this up, I'm going to turn this piece of paper over, and there are just some thoughts that we want to kind of put together regarding what we saw with differentiability and continuity. So if a function f, or whatever, g, whatever, is differentiable, then it is continuous. We say that differentiability implies continuity. So let's say you're given a problem and you're told, consider the function h. H is differentiable. Can I assume that then h is also continuous? Yes. Okay. Did they have to tell me that h was continuous? No, because we should know, and the takeaway from this lesson is that if the words are being used that a function is differentiable, then it is definitely continuous. Let's look at the other part of that. If a function f is continuous, it may or may not be differentiable. Think of the absolute value graph. The absolute value graph is continuous, but at its sharp turn, it is not differentiable. That's differentiability and continuity from the graphical perspective. We will investigate looking at differentiability from equations, but that'll be in a later lesson.